Electronics. Today's video we are going to see the questions from network analysis session. This is a part of network analysis subject preparation. We are doing numericals for network subject, and this is a video preparing for all technical assistant examinations of ISRO, especially for SSFC and SAC. Okay, so the first question is this: find the equivalent resistance. Okay, so we need to solve this connection of resistance and we need to find the equivalent of this particular connection. Okay, so how to solve this question? We should start the simplification or solving the equivalent from this side rather than starting from this side. It is a general practice. Okay, so if you see this connection, there are two 200 ohm resistors connected in parallel. We can do it without even using a pen in mind, because the numbers or the values of resistors are given in that way. So here 200 parallel 200. What will be the equivalent? Whenever two resistors of identical values are connected in parallel, means the value of the single resistance by the number of connection. Here it is 2. So 200 by 2, which is equal to 100 ohm. Okay, so this will be the equivalent of these two resistors, and you can replace this with a 100 ohm here. Okay, so here there is a 100 ohm and there is another 100 ohm connected here, and they are connected in which connection? Series. So total it will be 100 plus 100 is equal to 200. 200 ohm and 200 and 200 connected in parallel connection. So the equivalent is again 100 ohm is the equivalent. So the answer for this question is 100 ohm is the equivalent of this circuit. Okay, so whenever you are going to simplify such a connection or an equivalent, finding the equivalent of a large connection of resistors, which is the combination of series and parallel, you should always start from this side rather than going from this side. From this side you should start. Okay. So anyway, the answer for this question is 100 ohm is the answer. The next question is again a finding of equivalent resistance type of question, but this time it is a little bit tricky question. Okay. The approximate equivalent resistance between terminals A and B following an infinite ladder network. That is, if you see this network, it is actually an infinite network. It is going in an infinite way. This has been progressing infinitely. And if you see between these terminals A and B, there is a 1 ohm, there is a 2 ohm. Here again, this is being repeated in an infinite manner. 1 ohm, 2 ohm, 1 ohm, 2 ohm. Likewise, you cannot predict where is the limit. It is going in an infinite way. So how to solve this such an infinite connection? If you approach such a question, there are high chances that you may skip this question, but you don't need to actually skip the question. Just use your logic. So I'm going to find the equivalent between these two terminals, and I'm going to call that equivalent as Req. Okay, let the equivalent resistance between the terminals A and B be Req. And what is the normal procedure of doing such a question? First, we will see what is the 1 ohm. It is connected in series with this 2 ohm, right? But the 2 ohm is in turn connected with another set of networks, right? This is a series connection of 1 ohm and 2 ohm, right? So Req is actually 1 plus 2 ohm plus 2 ohm with another portion of network. This 1 ohm and 2 ohm is connected in series connection, but the 2 ohm is not independently. Another set of infinite network is also being attached to with this 2 ohm. So what is actually the equivalent of this 2 ohm and the rest of the network? Okay, so we have called this resistance, which is the equivalent between A and B, as Req. And now see this portion of this network. Here again, if you see, here again there is a 1 ohm, then 2 ohm, then likewise it is going in an infinite manner, right? So you can also call this portion, or starting from, if you are again starting from this portion, you can call it again as Req, because we don't know what is the limit, since it is going in an infinite way. It is actually Req again. if you see from this side also, it is again Req. Okay, that is, if you again call these points as P and Q, you can actually call the equivalent between this P and Q also as Req, because 1 ohm and 2 ohm, again this is been going in an infinite way. So we can again call this as Req itself. 1 ohm, 2 ohm, again it is been coming as 1 ohm and 2 ohm, and it is been repeated in an infinite way. So we'll call this much, that is this much, again we can call it as Req itself. So that is a key point to answer this question. And if you know that you can call this much as Req, you can answer this question very easily. Okay, now I'm going to call this portion as Req, and that Req portion or Req resistance, let that be the equivalent. Req portion is actually connected in what connection with this 2 ohm? In a parallel connection. Okay. So 1 plus 2 into Req by 2 plus Req. This is the equation to solve this infinite ladder network or infinite going network. Okay, so you are going to find the equivalent between A and P, and we are calling that as Req, and we know that Req is actually obtained with the series connection of this 1 ohm and with 2 ohm connected with another set of network. And if you see that network also, you can find that it is nothing but the replica of this much of network or this network itself, and it is going in an infinite way. If it had some limit, you could have solved that much to that limit, and then you could have found that equivalent, and then that equivalent will be in parallel with 2 ohm. But we don't know what is the limit. Since it is going in an infinite way, we can call this as also as Req. So that is a key point. Okay. Now let us moving on to the calculation of this question. I will remove this and I will keep it as the same. Okay. We don't need P or anything here. Okay. Just know that this is again Req itself. This much. Okay. Now I'm going to solve this for finding the Req actually. Is equal to cross multiply 2 plus Req plus 2 Req by 2 plus Req. Req plus 2 Req is 3 Req. 2 plus 3 Req. Okay, now take this and cross multiply with this one. You will get 2 Req plus Req square is equal to 2 plus 3 Req. Now take this much, that is 2 plus 3 Req to this side. So I'm going to rearrange and also write in a standard form. Req square plus 3 Req coming this side will be minus 3 Req. Plus 2 means it is a minus Req, then minus 2 is equal to 0. This is the equation we are getting. It is a 2-degree equation. Okay. So you need to find the solution for this equation to find what is actually Req. I'm going to find the solution. Okay. So rather than writing Req or anything, I'll write it in the form of x. X square minus x minus 2 is equal to 0. So the product is minus 2 and the sum is minus 1. So what is it? What are the two numbers? It is x minus 2 and x plus 1 is equal to 0, right? If you solve this equation, this x square minus x minus 2 is equal to 0, you will get x minus 2 into x plus 1. The product is minus 2 and the sum is minus 1. Okay, so x minus 2 and x plus 1. That is x is equal to 2 and x is equal to minus 1. You don't need a minus value for a resistance equivalent. Okay, you will get a positive value. You need a positive value as a resistance equivalent value. So the answer is x is equal to 2 is the answer. That is, you will get x is Req. So Req is equal to 2 ohms. Okay. So the equivalent resistance of these two terminals, that is for this infinite network, is actually 2 ohms is the equivalent resistance between these two terminals A and B. So this is a tricky type of question and I really hope that you understood how to do this question. You just have to identify that this network is actually going in an infinite way, and if you take this much of portion and if you take 2, the portion of the network which is coming as parallel with this 2 ohm is nothing but a replica of this entire network actually. So it is again because it is going in an infinite way. Okay. So it is again Req itself. So you have to apply the parallel equation for 2 and this much of Req, then plus this 1 ohm series. You will get the answer. The answer for this question is 2 ohm is the answer for equivalent resistance. Question is this: the current through 10 ohm resistor is dash. Okay, so this is a circuit. There are 2 loops in the circuit. We need to find the value of current through this 10 ohm resistor. This is 20 ohm, this is 20 ohm, this voltage source is 150, this is again 150, but the connection is in the reverse. Here the positive terminal is in the beginning, then here it is negative terminal. So we need to find the value of current through the 10 ohm resistor. The most simplest way to answer this question or to approach this question is by applying of nodal analysis. This is the node, central node here. We'll take that as N and let the voltage be V. Okay. I'm going to apply nodal analysis for node N. V minus 150 by 20 plus V plus 150 by 20 plus V by 10 is equal to 0. And if you solve this equation, the answer obtaining is V is equal to 0. So the voltage across this 10 ohm resistor is V, and that value is obtained as 0. Okay. Now, let us try to find the current. We know that voltage V is equal to I into R. Voltage is obtained as 0. So, current I, we don't know, it is I10 into 10. So, the value of I10 is equal to 0. So, 0 ampere is actually the value of I10. The current flowing through the 10 ohm is actually 0 ampere. Okay, so how to solve this question? It is by applying of nodal analysis. That is, we take this node, central node N, and we apply nodal analysis on this node. We'll write the nodal equation V minus 150 by 20 plus V plus 150 by 20 plus V by 10 is equal to 0. And we'll solve it and find that the voltage is obtained as 0. So the current I10 value is 0 ampere. The next question is this: for the network shown in figure, Vi of t is the input and I of t is the output. Okay, voltage is V of t, current is I of t. The transfer function I of s by V of s is dash. Okay, so we know that V is equal to I into R, right? So here these 3 elements are connected in what connection? In series connection. So the equivalent will be the sum of these 3 resistance plus a reactance of this L and this the reactance of this C. Okay, so you can write V of t is equal to I of t into R plus X L plus X C, right? You need to take the Laplace transform. Here you need to find the transfer function in the S domain. I of s by V of s you need to find. So, I am going to write the I of s by V of s equation, or you can write V I of s is equal to I of s into R plus the Laplace of this inductance, it will be L into S plus 1 by, for capacitance it is 1 by C into S, right? So, you need to find I of s by V of s. So, I of s by V I of s is equal to 1 by R plus Ls plus 1 by Cs. Okay, this is actually the answer, but you can rearrange and write in a more simplified way. Take this C of s, cross multiply and take it as common. So, I am going to simplify it. CS by S is the S domain. That is, we are taking Laplace transform. RCS plus LCS square plus 1. So this is the transfer function, that is I of S by V I of S. If you take, you will get as CS by RCS plus LCS square plus 1. Or in more simplified way, if you want to write, plus RCS plus 1. Okay. Now it looks standard. Okay, that is CS by LC S square plus RCS plus 1. Okay, so this is the transfer function I of S by V of S for this particular network connection of resistance, inductance and capacitance. Okay, so this is some questions which I have included in this video. I really hope that this video is useful for your preparation. Network analysis is very important subject concerning to any competitive examination of electronic, especially the numericals of network analysis concerning the solving of equivalent resistance or capacitance or applying of nodal analysis or KVL or KCL. All these are very important question areas of network analysis. So we have discussed some questions in network part 1. This is a part 2. I really hope that this video is useful. If yes, please do give it a thumbs up and also share this video with maximum of friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.